Okay, we're in the middle of the end of the EM. So we said this can be generalized to any distribution which has these two components, right? We have data and we have latent variables. We have hidden variables set which you don't observe. So this is very challenging to find the parameters maximizing this thing because we don't have the latent variables observed. So instead we want to do, of course, the same thing again. We want to just maximize the marginal likelihood, which we have written here. And we want to do this using something like EM. But now there is no K. That's a crucial point, right? Z here can be anything you like. So you can be very creative, having any kind of latent information, and from that generating any crazy distribution of data points. Anything is allowed here, P of X and Z. That's the only thing I assume, so you can have any generative model. Okay, what we're going to do is we're going to maximize the marginal likelihood, and actually we're going to again not do the complete marginal likelihood, which is, you know, something like that. But we're going to use again this purple thing, which is this model, and we're going to maximize that in every step. Okay, so what's happening here is that I'm claiming the generalization of EM is exactly that. What it is you don't know what your Z's are, these guys, but what you do is, so the problem is you don't want to have this structure of points, log, and then some more crazy stuff here. You don't want that, so you want to take the log outside. That's what you would like to do, and that's what's actually happening here. So, okay, let's be a little bit more precise. So, what we don't like is sum over points of the log of the expectation over these Z guys. That we don't want. So what we will do is something simpler. We will kind of exchange log and expectation. That's on a high level, and let's be more precise. So we are going to use the expectation over the latent variables. So you can think of this way, like you don't know what they are, right? So what can you do? Like the only thing you can do is basically to average over the latents. So just to take the expectation over them, because you do not have them instantiated. They're never observed, right? The only thing you observe is maybe their average, their expectation. So that's why we take an expectation here, and then here you have the standard log of this kind of joint thing. Okay, so let's convince ourselves that this is related to what we have been doing. So, for example, for GMMs, let's see. So then we have argmax, sum over all points. That's always the same. So what did you do before? What was this? What does it mean? Expectation over probability of Z. It's very simple. It's just actually this kind of marginalization happening. So now we're going to average over all possible values of Z. So now we're in a special case again. We want to study this special case when Z can only be K different things. And then this expectation here is very similar, very easy. It's the sum over K. So P of Zn being K. So if it has only K possibilities, then this expectation is defined exactly like that. That's the expectation of what? Of this value log So okay, what about, does this look any familiar to you? Here, this is the posterior, that's exactly correct. So, yeah, probability of the latent given the data. So, yeah, posterior. And in the special case that now I'm looking at, so now in that special case for GMMs, that's actually exactly the QKN. So, okay. So then what we have is the sum of these QKNs times the log, and that was actually exactly the EM as before. So sum over n, sum over k, over this QK stuff. Let's go back, check if that's the case. So where is it? Yes, that's exactly here. So this you can take together, that's just the probability of the point x, also prior times likelihood, right, times the QK. So that's exactly the local model we had, and this stuff here doesn't matter. So that's exactly what we've done before. So I'm just saying that this is why it's a generalization. So posterior times the log of p of x and z. Okay, and again the interpretation is the following, that so we kind of fill in, so the unknown information, the z's are not observed. What I'm doing at every step, I will just, so an important thing here is that, right, where do you build this model? So where have you made the approximation? I'm still maximizing over all the sigmas, right? I should maximize the full thing, like this and that jointly. But I'm not doing that. What I'm doing is that this one here I fix, right, to make my life much simpler, right? So now the variables are not inside and outside the log anymore, but they're just only inside the log. So fixing that for a moment, that's what EM does, and that's what makes life much easier. So fix that, find the next sigmas. That's the maximization step. And what's the estimation step? That's actually constructing this function, which you then should maximize in each time step t. Yeah, that's all. So we kind of average over the unobserved part of the data. Okay. Yeah, that's almost all we have on generative models. So this, yeah, and in this example we actually brought together a bit the optimization and the probability aspect. Okay, maybe good to implement it for GMMs, starting from your k-means if you want. And if you want, you can recap a little bit on what these names were for the probabilities, and yeah, try to understand surely why is this the interpretation that we just gave. Why does it make sense to run this algorithm from a probabilistic perspective? Yeah. Okay, we're done with EM. I'm happy about that. So then, or any questions? So on to some related, but yeah, some more unsupervised learning. Well, this one I'm going to see here is a bit debatable if it's unsupervised or supervised. Is a question on EM? Yeah. Yeah, so the question is that the algorithm does not provably converge, right? Because it's a very hard non-convex problem. So you asked if in practice it actually works, right? Because we didn't give a proof that it actually goes here, right? And that's an excellent question, and I mean, I'm also concerned running this algorithm if if this would do, but the thing is, it's like in k-means, right? It works amazingly in practice, right? It just works. But the theory we don't have. We do not have, in a theoretical worst case, right? The situation could really be bad. You could get stuck here. You could get stuck here. Like lots of bad things could happen. We don't have any proof that this has not happened. The only thing we can prove about EM, to the best of my knowledge, is that in every step you improve a very little amount. You never get worse. That's the only thing we prove. So that you will never decrease. That's the guarantees we have, but I'm not giving a guarantee that we go up there. And the problem is NP hard, because already k-means was NP hard. So. Yeah.
And also probably in practice it's like super hard to know if you're in a bubble, right? Because you don't know the bubble when. So it's kind of like how can you assess if you just...
Yeah, you're also saying that we don't really know if we are done, if we've converged. And again, I agree, it's true. So the only thing you can do is you can look at the likelihood and see if you're happy with it. But it's pretty difficult. Also, you're not sure about how many Ks you should choose. So maybe you try a different case, and then there's nothing else than, I mean, this is unsupervised learning, right? So it's very hard to give a number to how good you are, right? So you really, once you have trained a model, you're probably going to look at it or use it for a second task to see if you did some good unsupervised learning or not. But yeah, it's not easy. Okay, but still, I mean, unsupervised learning is really cool because this is very task independent. We can use it for anything afterwards. We hadn't specified that we train it for a particular task, right? We have trained it kind of in general, so on the data alone. So here's something which is related to unsupervised learning, but not quite, so it's a bit in the middle. So we want to look at matrix factorizations, and I introduced this a little bit in the beginning, like when we started unsupervised learning, we said maybe we have users and movies, and maybe, so what this means is that user N gave some stars to movie D, for example. Well, you can use different indices if you want. So this is some data which is given. So this you could call labels. We have some targets. What is the task? The task is to predict all the stuff we don't know, right? So all these unknown entries. We don't know if that user might also like, so the user only likes one movie, but maybe he or she might also like that movie or not, depending on all the information we have from that user and also all the information we have about all the movies. So movies are rows, users are columns in this case. Yeah, so that's the task, to fill in all these unobserved entries. And to make this formalized, we're going to call this the X matrix again, and we are trying to approximate this entry by a product of two matrices. So that's what we're going to do. So we have kind of a matrix. We have, let's say, okay, I'll just give the idea here, right? You're trying to approximate this X matrix, but that's not all the entries. Trying to approximate this with a matrix product. But not everywhere, but only the wide entries, only the ones which are observed. That's kind of the task. Then this reminds you a lot of the k-means. Maybe, do I have k-means somewhere? No, I don't. Yeah, we discussed this at the beginning of unsupervised learning. But for k-means, we actually used a bit of different notation. We used x transpose. We were able to write it as w times z. Then this was consistent that data points in the X matrix are rows. That was for k-means. And now I'm going to just very slightly abuse notation. I'm going to, from now on, when I talk about matrix factorizations, I will talk about this data matrix here, which is the transpose of what we had for k-means. But it's just a naming. So, because here it's not clear what is a data point anyway. Is a user a data point or is a movie a data point? It's not clear, right? And also we don't care. All we care is that we are given some matrix entries. It really doesn't matter what are the interpretations of rows and columns, but we're given all these white matrix entries and we're trying to complete the matrix. And just so if you go back to k-means that you're not confused there will be a transpose here, but now I'm not writing this transpose every time. So, okay, this is what we're going to do, because this is a general principle. Given any matrix, approximate it by what? By some w times z. Right, so maybe X has this shape. And then, so there are kind of three interesting shapes. This is the long direction, is the same as here, right? Then you have the other dimension of X is the same as here. So that's just a matrix multiplication. And then that thing here, that's K. So that's the number of latent factors, or kind of hidden variables, which you can choose. So let's say we're trying to just use 10 real numbers. So every row of this W matrix, or every row of Z, actually this is a row of Z, they all have 10 entries. And what is their purpose? The purpose is that these 10 entries from W times the corresponding 10 entries from Z. So this is the D's entry of W, right, from the movie D. And you're multiplying this with the end entry of Z. So the goal is that this inner product of two vectors is approximating what you observed. It's approximating the true value, which is 3 stars, between 1 and 5. So that's the idea. What is the learning? The learning is to find these W's and Z. So it's important here that, I mean, X can be 1,000,000 by 1,000,000 or more, but the W's and Z's, well, the yellow and the green directions, they are still 1,000,000, they are huge. But the K is usually much smaller, right? So you can learn a much smaller number of parameters to approximate some really big matrix. So it's actually in this real-world application where it's the Netflix prize competition or so, they really used a K which was about 30 or 40, but not 1,000, right? So if this is only 30, but let's say you maybe have 10,000, what was it? They actually had 20,000 movies, so 20,000 movies. They had, I think, if I remember correctly, 100,000 people, and then how many white entries which you observed? That's maybe a lot. So I think they had 100 million, if I'm correct. And actually, that's a very similar data set as you use if you choose to do this recommender system project as your second project. And it's derived from this data set. Okay, that's the task. So find W and Z, which approximate the X well. So it's a very simple task. And there are some different variants how you define this to be close, right? And that's what we're going to look at a little bit. So here is the problem again. That's exactly what I wrote. That's our task. And now if you want to formulate it as an optimization problem, then this is basically what you would get. So what is it? So the question is this, what are we summing after? So what we have here is the squared error. So the D and N here only goes over the white entries where we do have the information. And what it does is it checks this, how many stars did we observe here, right? So movie D, user N, has given 3 stars. And here is my model. The model predicts that, just that the n's, the d's row of W. Maybe I use this MATLAB notation to be sure what's rows and what's column. And this is going to be multiplied with the d's row of Z, with the n's row of Z, which is actually the n's column of Z transpose. They get multiplied. And that value is hopefully approximating our 3 stars. If it's too high, if it's too low, we punish the squared error. That's a natural objective, and omega is just the set where we do have observed ratings. So maybe usually like 99% or 99.9 is not in the observed set, right? So everything is gray, but like 0.1% is maybe where you do have the information available. So that's the white entries, and you only have those two to train your model. Then. Okay, so now we already have our cost function and we have defined our model. So again, the only thing you have to make here is, it's a bit similar to k-means, right? There's one parameter which you have to choose, and that's how many columns how many latent parameters do you have, right? So again, W and Z transpose, they have the same dimension here, so that they can be multiplied. Okay, choose this hidden dimension to be rather small. That makes a lot of sense. Any comments on this model?
How do we combine a model like this with metadata?
You're asking, so okay, what I described has no information about a particular movie, right? The only data is the stars, right? I have no idea that this is an action movie or that George Clooney is playing in that particular movie or not. I have no such information. I also have no information about any user, except that they gave 3 stars to that movie. I think your question was, if I did have additional information, could I improve my model? So could I add a new feature that, hey, that movie there actually has George Clooney in it, and that user there likes that or not? And yeah, what would you guys suggest? How could this be done? So if you have some fixed additional information for all movies and for all users, what would you do? So.
Just add an additional matrix.
Add additional matrix, but how? So I mean, now the whole W and the whole Z, they are 3 parameters, right? But if I have additional movie information, then that's some fixed bunch of numbers. How could I add it?
I'll just add columns on W and then coefficients.
Yeah, so add it as new columns, that's what you're saying. So W, let's be more precise. So W is what you call the movie matrix, right? So this is the movie matrix, this is the user matrix, the Z. So what you said is, okay, this is the movie. We said it's this additional information on each movie. I could put it here as fixed numbers. And that's exactly what you would do. So if I do this, does it still work now, or does something has to be adjusted?
Number of columns in Z.
So now you also need to add stuff to Z. And what will you put there? You don't know what to put. So that you would actually leave free. So now I just added more information about movies. And I added more, so this stuff is fixed. It's fixed hard numbers, hard-coded. But the yellow stuff is free. That I will actually going to learn. And this is going to be for each user how much they like the movie attribute. So whatever actor is playing in each movie, then you put a 1, and otherwise it's a 0. And the yellow stuff here, you can almost see it. That's going to learn for each user if they liked it or not. That's exactly what you're going to do. Then you would do the same thing if you want to add features about users like the age and stuff. Then you would put more fixed values here in a new column of Z. And you would need to extend the movie matrix to have more parameters here to learn weights which can use this movie information, user information, sorry. Okay. Yeah, that's, but maybe we are going a bit too far, yeah?
So if you actually want to add like actors, let's say, can you put like numbers for each actor? Because I feel like this is a little bit wrong because you cannot say like one, like George Clooney is 1 and I don't know, De Niro is 2 and stuff. Because
sure, no, but the actors you could very easily add. So you will just add one new feature for each actor. So if that actor is in that movie, you put a 1, and for all the others actor, it's 0. So this works well. Also, if you have like a genre of a movie, if it's an action movie or not, then you will have one new column indicating action movie, yes or no.
So yours needs to actually like increase so much because you said like 30K is like 30, 40, which can actually increase.
Yes, there. So you're right. I'm only using K equals 30. You're saying there are a lot of possible actors, so I would add so many new columns to the black stuff here. So that's true. But this is fine, this still works. You wouldn't actually need to think to add regularization. And we will discuss what regularization means in such a model a bit later. But let's start with the simple model first. You guys are jumping ahead. But this is a simple model, and it's not only for recommender systems. So this is much more general. So you will have many different cost functions, which can depend on a product of two matrices, right? Multiplying two matrices is a super natural and easy thing to do, right? It's a very natural model. I would say it's the most natural model after the linear one, right? Linear was even simpler. Linear model was convex. This one is now having a product of two things, but that's like the next step we can do. And this works really well. We just have to discuss a bit now how this thing can be optimized. How do we find the W and Z matrices? How do we find the movie matrix and the user matrix? User. Sorry for the writing. Okay, but the interpretation is clear. So the model is simple. What you could ask now, this cost function L, is it actually convex? And is it identifiable? We had this discussion before. So that means, is there a unique model? Is there a unique W and Z which will maximize it or minimize it? So some people say no, but let's think about convexity first. Okay, is this a convex model? Who would say it's non-convex? Who would say it's convex? Who is undecided? So what model am I talking about, right? This one. So what's the simplest case? So maybe it's simplest if you have only very small n and t, right? So if w and z are very small and simple, then it's a good idea to think w and z are very small, so then how does this thing behave? So, and I'm just measuring basically how close you are to the x. Okay, so we ask if this is convex in the full variables, right? We're optimizing both things, the w and the z's together, so the parameters are w and z together. That's our parameters. My question here is, that's what it means, jointly convex, right? It's convex in the parameters z and w. Okay, so here is w, here is z, and let's say we look at a very simple function, loss of what's the simplest function I could define on these things? Actually, if they're only 1 by 1 matrices, then this is the easiest thing I could consider. Well, it looks like a nice problem. It's not too hard, right? Just two matrices get multiplied very nicely. But even if these are just 1 by 1 matrices, so this live in R1, and also Z lives in R1, even then this is a non-convex function. So this is the identity applied to the product of two numbers, so just the two numbers. So is that convex? Actually not, because here it's positive, here it's also positive. When they both have a minus sign, then their product is positive. Here it's actually negative, and here it's negative. So I'm claiming that this is a non-convex function. So the way it looks like is a bit like this. So this is a bit the level sets of this thing. So here it becomes bigger and bigger if you go that direction. If you go, and if you are in the negative orthant, then you can go up to, minus infinity here, and here you go to plus infinity, and so on. That's the idea. So why is this non-convex? Can you see it? Can you give me an example, or how would you show that this is non-convex? So. Oh yeah, you're asking if there shouldn't be a square. Yes, sorry. This, what I'm describing here, is a bit a slightly easier model or more general. So I'm describing the class of all these things, and I'm only, the example I show you is not about the square. The example I show you is about L is the identity. So okay, I should make it more clear. So L of W and Z. What is it? It's a function of the product. And what I showed you is the example is when I define F to be the identity. So. And if it's the identity, then this is my example. But you're right, this is not exactly what we had with the omega. So, but even in that simpler example, that's even simpler than the squared loss, even then it's a non-convex function. So the thing here to observe is like, what's the difference here? Like L and F, right? So F takes one matrix. It depends on the product. And L takes two matrices. So if you ask about convexity of L, that's a very different thing than to ask about convexity of F. So F here is very simple. It's convex. It's also convex in what you are saying. If it would be the square is convex. That's fine. So that's F is convex. But L is not convex, because now I'm looking at the two variables, or like two groups of variables together. And in these guys, it's not convex, even in this special example when F is super simple. So how do I show that? How would you see that? What's a counterexample? How would you prove that this function is not convex? Exactly, you would draw a line. You said this one, top left, bottom right. So that's exactly what you do. So here, top left, it's negative, right? It's maybe minus something. Here it's also minus something. But in the midpoint of this line, somewhere in the middle, the function is 0. So what it actually looks like on this line is something like this. Right, so the function is not convex. It's violating this condition. So the answer is no. It's not convex. I only showed it for the identity, but you can actually also show it for the square, but that's a bit harder to show. I'm not going to do that. But you can think about it. So okay, so it's a bit hard to optimize in general, even if the model looks really simple. Then that's one question we had. So convexity. Now the second question is it identifiable? If you have a solution, is that solution unique? Or is there another one which gives you the same optimal value? What do you guys think? So let me give you some optimal solution. Let's say this particular W and Z is optimal. Now, can you find other optimal solutions if I give you that? So remember, here is your F of W and Z transpose. Yeah. Exactly. So if this W and Z were optimal, you're saying I could look at a constant times W, lambda, and I could look at 1 over the constant times the other matrix. So here is also optimal. Okay. Whenever you have a solution, you can scale one of the matrices by 1,000 and multiply the other by 1,000. So the product is completely unchanged. But the W's and the Z's have changed massively, right? So it's very non-identifiable. But this is not necessarily a problem. I mean, sometimes it depends. If you're looking for a unique solution set, but usually what we are looking for in machine learning is to look for good solutions, right? And good is measured in this quantity here, the cost function. And no matter what trick you do with this scaling, the cost function is the same, right? So you're still having a good cost function. So yeah, these are two important properties. It looks very simple if you see it first, but it's quite subtle. So it's not completely obvious if it's very easy or rather hard to optimize. Actually, if this set omega, like the entries which you are actually observing, if that's all the entries, right, then what's the cost function? Can anybody give me that cost function in that special case? Then I sum up over all the entries, the square difference. Have you seen that before? Yeah, that's exactly, that would become the Frobenius norm of, so I maybe need some space, that would become the Frobenius of how far you're away from your x. You'd like to be close to the x entries, and now I'm talking about all the entries. So if omega is all the entries, then the cost is equal to this. So you're asking what low rank matrix is closest to my x. And that's exactly what you will get by the singular value decomposition of x. So that's a very easy special case. So we're actually going to do this next week to explain the singular value decomposition in detail again. You have seen it already though. But you can trust me that if this is rank 30, right, he has 30 columns, then the optimal solution to that special case, all entries, that solution is the top 10 singular vectors, the top 30 singular vectors, if you have that particular K. So it's a closed form solution, which is very nice. However, if omega is not all the entries, which is what we actually care about, right? If we have all the movies ratings observed, then there would be nothing to do, so that's completely uninteresting here. So if the pattern of observed ratings is general, it can be worst case, then this problem suddenly becomes NP hard to optimize, which is quite surprising because it's so easy when omega is all the entries. It's actually very hard. Even for k equal 1, it becomes NP hard to find the minimizer of this thing. Right? Not for omega being full, but it becomes hard when omega is a particular pattern of the observed entries. So that's the matrix factorization problem for, it's also called matrix completion because you're filling out these entries. It has lots of applications. So not only recommender system, but you could also think of like, maybe you have images which have missing patches and stuff, then you could use this to fill in some missing information. And it's actually also increasingly used in learning representations for other things. Not only, so what we have done here is we have learned a representation for each movie and for each user. For each user, we learned 30 numbers. For each movie, we learned 30 numbers. So now we have a very interesting representation for each user and each movie. And that's the powerful thing about this, that it can be used for representation learning. And so that can also be used for text. So to learn representations of words. So, okay, yeah. Same story as with k-means. So choosing how many latent variables k you want to have, that's not such a clear story. There's no very precise answer to give here. Again, in this competition, which was a few years ago, where there was $1 million for the best recommender system doing that, the best algorithm. And there they used exactly what I described here, this cost function, and they used about 30 or 40. In practice, you will have to try different values. And this is what happens. So because we said you learn a representation of each movie. So that's the W matrix, right? And there is also the Z matrix, but I don't care about that one so much. But here you would have a user representation. But let's look at the movie representations. And so if K would be 2, then you could get a little bit of picture like that. So you could get a point for each movie, right? For each point, for each movie, you have learned 2 numbers, right? Number 1, number 2, if K is 2. So now you can actually look at this. So this is, you have done some kind of almost unsupervised learning to learn something about the movies themselves, just from these ratings. if you plot them, you really get good clusters. So you can maybe look it up if you have time. This works very well. The movies which are of a similar style get really clustered together, despite the fact that we have used nothing about any information on these movies. We have only used this, how many stars have people given to it, and was it actually the same people or different people. This is actually not k equal 2, but this is a larger k, and then later on they have been projecting it to 2 dimensions to simplify the visualization. Quick question, then we are almost done.
So if you actually add like randomly, let's say 1 column or like multiple columns for some movies, is it going to be better? Because you
So yeah, the number of k is kind of an overfitting question. If the k is very large, you will get a perfect fit. You will get a perfect star ratings, but only on the training data, right? So on the test data, you will not be good. And if you pick a smaller k, then you will do less overfitting. You have a more restrictive model, so on the test data, you will be better at generalizing. And this you can actually see in the exercise. We have template code for you. It's all ready to play around, and if you want, you can also do this as a project. But there are also 2 other projects. Don't forget about that. And we will have also more information about the other project next week. So you will have template code for all the projects. Okay, I see you on Thursday, and if you have more questions. Yeah.